Okay, so welcome to the last lecture of this CS479 machine learning for 3D data. And today we are going to talk about some new topic. Before I get started, where are we supposed to print is your poster? So we are going to print your posters. So you don't need to print your poster yourself. So if you submit your poster by this Wednesday, we are going to print all the posters, but we can also ask you to attach the poster when you present in the poster sessions. So that's the thing. Any other questions for the poster sessions? All right, so let's get started. So last time we discussed some kind of new topic, which is about the 3D object segmentation and also the detection. And we are also going to discuss another topic in this last lecture, which is revisiting the basic idea of like the point cloud processing using the neural net. So we discussed some kind of the bunch of the ideas in terms like how to make some kind of the encoder of the point cloud. So the basic idea was the point net, and we also discussed the point net plus DGCNN, how we can also make some kind of the variance of the point net. And when we basically design some kind of architecture to process the neural network, basically there are some kind of two things that we discuss as kind of the main kind of the aspects that we need to think about. So basically the two things was basically that we are basically taking a set of the points, basically some unordered kind of information as the input. So here the question was basically how we can basically properly handle this kind of the set data in terms of like achieving the permutation invariance and the equivariance. So that's kind of the main aspects that we also discussed with the point net. And also the other thing was basically rotation the invariance. So basically how we can also achieve the rotation invariance. So it's basically the one of the main aspects in the design of the point net. So for the invariance and the equivariance, basically the main aspect was basically this kind of thing. So when we also change the order of all the input data, so in the given the point cloud, basically when we randomly permute the order of the points, how we can guarantee that the output of the point net becomes the same. However, we basically change the order of the points. So that was basically about the permutation, the invariance. And also the permutation, the equivariance was basically about basically how we can also get the set of the kind of data as the output in terms of basically preserving the order of the points. So 1 second. So let me change the Zoom setup. Sorry, 1 second. Yeah, so basically also for the question about the permutation equivariance was basically the case, like when we get some kind of the set of the data as kind of the output, how we can also preserve the order of the input data in the output of the neural net as well. So that was about the permutation, the equivariance. So the invariance was basically the important aspects for the problem like classification. So basically when you classify the input points, regardless of the order of the points, we wanted to get basically the same scores for each of the class D labels. So that is basically the things that we wanted to achieve the basically permutation, the invariance, and also the permutation equivariance is basically important for the segmentation. So if we also change the order of the points and the order of the basically all the labels should be also basically preserved depending on the basically the order of the points. So that is also kind of the aspects for the permutation, the equivariance. So basically, to achieve this kind of the two things, the permutation invariance and equivariance, what we did in the design of the point net was basically using the shared MLP, and also using the pooling layer, using some kind of symmetric function. So basically, here the idea was that we are treating each of the point as kind of all the independent data, and then after processing them, we are basically aggregating all this kind of information using a kind of a symmetric function, like the max function, in terms of that we get the same outputs without just taking any kind of ordered information for the points. So that was the basic idea for the permutation, the invariance. And to achieve the permutation, the equivariance, while also basically utilizing some kind of the global information of the input, the point cloud, the idea was basically simply concatenating the local feature and the global feature in a way that we can basically utilize both the global and the local information while still achieving the permutation equivariance. So this was basically very simple, the idea in terms like how we can handle some kind of the set data using the neural network. And also the other thing was basically how we also achieve the rotation, the invariance. So here the question is that we want to basically classify, for example, the chair as the chair. However, we basically rotate the input point cloud in some kind of any arbitrary rotation the matrix. And for that, basically the component that we used in the point net architecture that you also might just try to implement in your assignment one was basically having this kind of the spatial, the transformer, the network, which is basically adding some kind of small component in the neural net in terms of that the network can basically predict a data-dependent rotation the matrix in a way that we hope that the input point clouds would be basically aligned into some kind of the canonical reports. So that's kind of the basic idea. But obviously there are some kind of the downsides of this kind of the small D component. What are the downsides of this kind of the component in terms like achieving the rotation the invariance? Do you remember what was kind of the some limitations of like this architecture? Question one. Yeah, so basically, I mean, it can be also slow, but also the more the critical thing might be is that we are basically applying the rotation to the input point cloud in a way that all the input points, the clouds can be basically aligned into some kind of the canonical reports. But basically, the obvious, the limitation is that there is no guarantee for this kind of alignment. We just hope that the neural net to run this kind of the rotation in a way that the neural net can run everything, kind of like more efficient way. Then probably basically aligning all the points into the canonical reports might be the best way to achieve some kind of efficiency in the learning. Obviously, basically there is no guarantee to achieve this kind of alignment. So this was kind of the first limitation. And also the second limitation is that while we are basically predicting a rotation matrix as kind of the 3x3 matrix, I mean, this is not exactly the limitation of this component, but if we just use the very naive way to apply the spatial transformer network, the thing is that also there is no guarantee to predict a rotation D matrix. So what we typically do in the point net implementation is that we are predicting a 3x3 matrix and having this kind of the regularization the loss in terms of that the matrix becomes a rotation D matrix, but obviously just having the regularization does not guarantee to basically predict even the rotation D matrix. And this second issue can be handled with some kind of different representation of the rotation D matrix. But the first problem is basically the biggest problem, basically how we can guarantee achieving some real the rotation the invariance is kind of the key problem in the point net the architecture. And achieving the rotation the invariance is actually really big issue in many kind of the real world problems. Because for many kind of some kind of the benchmark the setup, we are playing with some kind of some well-known data set like the ShapeNet or some kind of the other 3D data set, where basically all the 3D models are basically aligned into some kind of the certain orientation. So if you basically, I'm not sure whether you have any chances to basically see all the 3D models in the model net or the ShapeNet, but if you actually see all the chairs or all the airplanes in this kind of the data set, then you will be able to see that all these 3D models are basically having the same orientation, basically having the same different base kind of the views for all these 3D models. But for many kind of real world cases, basically if you deal with some kind of the scan data or some kind of the random 3D models in some kind of the online repositories, then you will see there are actually lots of the cases that the objects or some 3D information that you have are basically not aligned in terms of their orientations. So basically handling this kind of some random orientation is really kind of the big problem in many kind of some real world cases. So the thing is that if we have this kind of some 3D objects with some kind of the random orientations, the thing is that without any kind of some components like achieving the rotation, the invariance or the covariance, the neural net will basically see that these kind of the identical 3D objects as kind of some all the different the 3D data because their orientation is basically different, right? So if you basically like see all these kind of 3D models with the point clouds having basically 1,000 or 2,000 kind of the points, having all the basically the 3D coordinates for each of the point. If we transform them using some kind of the rotation the matrix, then it becomes kind of a new point cloud with all different numbers. Then from the neural net perspective, the 3D the point cloud becomes just kind of like completely different 3D the point cloud. So basically, there is no guarantee that you're gonna basically get the same the results when you basically apply any kind of the rotation or some transformations to the input data. So that's kind of thing. So we want to basically achieve some kind of the rotation invariance and equivariance in some in our the design of the neural network in terms of that. Actually, that's also the way that the human basically perceives some kind of the 3D models. For the human, basically, however we basically rotate all the 3D models, basically all the rotated chairs are basically the same chair, right? So basically how we can teach the neural net in this way, in terms of the way that we human perceive some kind of 3D, some information, it's kind of like one thing that we want to achieve here. And also how we want to basically generalize all some kind of the information that we learn from some kind of the some online repositories with some kind of the online 3D models might be also kind of things that we want to achieve. For example, we might want to train some kind of the classification network using the ShaneNet, the 3D the data set that we have. And if we want to basically utilize this kind of information to classify some kind of the real some 3D scan the data, then typically we might want to basically achieve this kind of the rotation, the invariance and the equivariance, because otherwise you will need to basically first align the given the 3D models in some kind of certain ways. So without basically having this kind of some pre-processing, aligning all the 3D data, how we can directly apply some kind of the pre-trained the neural network with some kind of into some kind of the real data is kind of something that we want to achieve here. So how we can achieve the rotation, the invariance, and the equivariance with some kind of some neural network. So let's think about some easier way without making any kind of the modification of the given the neural network. How we can achieve these kind of things. Do you have any ideas for this? So let's think about that. We are having a point net without any kind of specialty transformer, which is not having any kind of the property for the rotation, the invariance. And we want to make a kind of the classification, the network of the 3D models, like classifying the input as kind of chairs, airplanes, whatever kind of things. And we assume the case that the input 3D models might be basically randomly rotated. Then without making any kind of the big changes in the neural network, how we can achieve the rotation, the invariance for this kind of case. Any ideas for this? Yeah, so one of the simple idea for this might be is basically data augmentation with some kind of the random rotation. So basically the thing is that we want to teach the neural net in terms of like making the neural net to see some kind of the cases that 3D models are basically rotated, right? Then the simple way that we can do is that given the 3D models that are all aligned into some kind of the canonical depots, we are applying some kind of a random rotation to all the 3D models in terms of basically let the neural net to see basically all these kind of the possible poses of the 3D models. So that can be a very simple way that we can basically train the neural net while achieving some kind of the rotation, the invariance, without making any kind of big changes in the neural net architecture. And this is actually quite effective way. Actually, this works in many kind of the cases. But then what would be kind of a limitation in this case? Simply data augmentation in the case. If we basically teach the neural net while basically applying some kind of a random rotation, then what would be kind of be some limitations in this case? Yeah, obviously the problem might be is that there's no efficiency here, right? So this is actually the case that we are populating the training data, like augmenting the training data in terms of basically increasing the size of the data to be learned in the training the process, which means that it requires larger the capacity of the neural net, because the neural net need to basically memorize way more the diversity of some kind of input data, and also it will take way longer the training time. So that's kind of the big limitation. And also this does not guarantee to basically learn the rotation, the invariance, or the covariance in terms of that. We are basically teaching the neural net that these two are basically the same thing. So when you basically rotate the 3D model, we are teaching the neural net that basically whether you have this one or some kind of rotated 3D models, these two should be resulting in the same the output. So basically, this is basically some statistical way to basically teach this kind of the rotation invariance or the covariance. But this does not obviously guarantee to basically give the same outputs in this test time. So the other way around, which might be less naive approach, might be basically this kind of multi-view approach. So here the basic idea is that we are not basically treating all the kind of the different bodies of 3D models as kind of different data, but actually we are making some kind of all the random rotations and making the set of all the different bodies as kind of a single data point. Does it make sense? So when you have this kind of the airplane, instead of basically making all the different bodies and treating them as kind of the different 3D data, we are making the set of the different bodies of the 3D data as kind of like one single data point. So whatever kind of 3D models that you have, you are now having a set of set. So each of the point cloud is also a set of the points, but you are also having a set of the point clouds as well, with some kind of different bodies. So we basically let the neural net to basically see all the possible bodies of the 3D models as kind of input in terms of making this kind of set of the set. So this is like slightly more the effective way in terms of basically somehow guaranteeing some kind of the rotation, the invariance, and the covariance. But this also takes some kind of the requires some kind of more the capacity neural net in terms of basically making a single data point into a set of set, which is basically making one single data point that's kind of like much larger size of the data. And also there might be some kind of precision errors in terms of that. We also need to sample a certain set of the rotations in the 3D rotation this space. So which means that depending on like how many samples of the rotations that we have, there might be some kind of the precision errors caused by some kind of like having some discrete the number of the samples of the rotations. So these are some kind of real simple approaches in terms of like achieving the rotation, the invariance. But compared to this, actually we want to make some kind of the better architecture, which is basically lightweight in terms of that we are avoiding this kind of some data augmentation. So we also want to make some kind of architecture that can be actually applied to any kind of the point cloud processing architecture, basically into any kind of the variance of the point net. Without making some kind of a specialized architecture to achieve this kind of the properties. And also the other thing is that we also want to make all the process to be learnable in terms of having some sort of the learned features, not using some kind of the handcrafted features. So to this end, we are basically discussing some kind of the neural architecture, which is the vector neurons. So based on that, what are the applications that we can do? So basically, we can apply these kind of architectures for the classification. So classification will be the case that we want to achieve the rotation, the invariance. And the segmentation is also another case that we want to achieve the equivariance in terms of if you change the order of the points, the order of all these semantic labels should be changed. And also for some kind of the reconstruction the tasks, we also want to combine the equivariance, the encoder, and also the invariant decoder in terms of making some kind of the rotation, the invariant, some kind of the reconstruction the process. So that's basically what we want to achieve using this kind of the neural architecture, which is the vector neurons. So let's briefly get into the idea of this kind of the neural architecture. So here the idea is that we are not going to make some kind of the completely new architecture, but we want to actually just transform the given the point net without the special transformative pulse in terms like achieving the rotation, the equivariance, and the rotation, the invariance. So how we can do that? So that's the basic idea. So let's see, briefly remind the architecture of the point net. So this was basically the case that we are having some kind of the stacked kind of MLP, which are actually the shared MLP for each of the point, and having the pulling the layer at the end, and also concatenating this into the local features, and having also the shared MLP as well. So this was kind of simple architecture of the point net. So, and if we see each of the layer, then each of the layer of the point net can be seen like this. So basically, we have some kind of the sort of the C-dimensional vector for each of the point, stacking all these kind of C-dimensional vectors for each of the point, and then also getting the another feature for each of the point, which is the C prime dimensional feature. So we can ignore the time one here. Then what you can see is that given the feature vector for each of the point, which dimension is the C, we are also getting some kind of the another feature vector for each of the point, which dimension is the C prime, right? So this was basically the case that we are having some kind of the layer for each of the feature vector. So another kind of, yeah, the same thing here. Basically the here N denotes the number of the points, and the C denotes the number of the input and the output the channel. So basically the dimension of the feature. So for each of the point, we are having the C dimensional feature. And so this is just like for about the notations. Oh, sorry, something has broken in my slide. So given the point cloud, so here this Z is the point cloud. For each of the point, so these are some kind of feature for each of the point. We are having some kind of the feature vector for each of the point. And instead of like seeing the features for each of the point as kind of the vector, now we are going to see this kind of the features for each of the point as kind of the list of the scalar values. Basically the same thing, but we're gonna see what's the meaning of that is in the next slide. So for each of the points, we're having this kind of the scalar list of features in terms of like having see the number of the scalar the values like this. So this was the setup that we are basically treating each of the layer of the point net as kind of a function. And here, what we want to do is that we are basically transforming this function in a way to basically handling not just the scalar values, but actually the vectors. So what we are now going to do is that now we are transforming each of the layer in the point net in terms like lifting the neural representation into the scalar values into the vector, the values. So what we do is that now we are having the C number of the three-dimensional vectors for each of the point. And also we are now transforming this kind of the set of the features like this in terms of now having the C prime number of the three-dimensional vectors for each of the point. So in the next slide, basically what we can see is that as the input, we are also having a set of the feature, some kind of features for each of the point. And here each of the VI indicates the feature for each of the point. And as the feature of each of the point, what we are having is that we are having the vector list, the feature. So now we are having the C number of the vectors as kind of the feature for each of the point. So this is kind of the way that we are seeing the features of the point. Does it make sense? So in the point net, what we had as kind of feature is that we had the C dimensional vector as the feature, right? And we could consider that like that's the case that we are having the C number of the scalar values. So we are having the list of the scalar values, having the C number of the scalar values as the input, and also having the C prime number of the scalar values as the output. And now we want to consider the case that all the features are now represented as the three-dimensional vectors. So here is the vectors of the three-dimensional vectors. And as the feature, what we are having that we are having a list of the vectors. So now we have the C number of the vectors as the input, and we want to make a neural the layer of the neural net, which returns the C prime number of the three-dimensional vectors. So that's kind of the modification that we are making in this case. It is clear? Yeah. So in the classical, the point net, the case, for each of the point, we have the C times 1 the number feature, which is the case that we have in the C number of the scalability values. And then basically each of the layer of the point net transforms into this into some kind of the another the scalability list, which is basically having the simple number of the scalarity values. And now we are having this kind of the setup that we are having the C number of the three-dimensional vectors, and also the layer, each of the layer of the neural net is basically transforming this into the C prime number of the three-dimensional vectors. So this is the setup that we consider here. Is it clear? So let me know if this is not clear to you, because if you are basically confused at this point, then you cannot follow anything in the rest of the lecture today. So these are basically some kind of the notations. So here basically this Z indicates the data for the entire point cloud, right? And for each of the points, we are having this kind of the features. And in this scalar feature-based system, what we have is that basically we have the same number of the scalar values. So each of the neuron that we see here is basically a scalar value here. For each of the point and the channel, we are having these scalar values. But now we are transforming this into the vector feature-based system, which is now having the V here as kind of the data for the entire point cloud. And for each of the point, we are having a list of the three-dimensional vectors. So for each of the points and the channel, we are having the three-dimensional vector. So this is the case. I still don't understand how the vectors are translated to layers. Is there a 2D layer in PyTorch, for example? No. So we're gonna see how we're gonna basically process all this kind of the three-dimensional the vectors for each of the layer. Yeah. So yeah, we will get to that in the next other slides. Any other questions here? So it's kind of like, changing the way that how we treat all this kind of the input, the information, and also the output information into the vectors. So everything was basically some scalar-based kind of the things. So the key thing is that we are seeing the feature, the vector for each of the point, not as the vector, but as kind of the list of the scalar values. In terms of the now we are replacing all these scalar values into the three-dimensional vectors in a way that now we are having this kind of the sort of the 2D array, having the C times 3 features for each of the point. And then also making some kind of transformations. So if everything is clear to you, then now the question is that, so let's think about this kind of the function, which is representing the layer in the neural network. And let's say we want to apply some kind of any arbitrary rotation matrix DR. So let's think about the case that as the input, we are having this kind of the n times c times 3 kind of information, which is basically having the n number of the points, c number of the channels, and for each of the point and the channel, we are having the three-dimensional vector, right? And we want to apply some kind of the arbitrary rotation into the given this kind of input information. Then how we can basically express the rotation, the equivariance with this kind of function and the rotation the matrix. This is the another quiz. Do you have any answer for this? So here, please check out that our notation is basically having the V. V is basically a kind of a tensor of the n times c times 3. And then as the output, we are having the m times c prime times 3. So yeah, here basically we need to multiply the rotation matrix on the right-hand side because of the dimension here. Then what we can see is that so applying the rotation matrix to the input point cloud is basically multiplying this on the right-hand side, right? So when you basically apply the rotation matrix to the input, the point cloud, this should be the same as kind of like first feeding the input to the neural net and then multiplying the rotation matrix on the right-hand side, right? So that's basically what we want to do as kind of the rotation equivariance. So whether you apply the rotation matrix before you feed the information into the neural network, or after you basically apply the rotation matrix to the output of the neural network, the output should be exactly the same. So that's basically what we want to do as like achieving the rotation equivariance, right? It is clear? Any questions on this? And also the thing is that for the participation score, you need to provide some kind of some reasonable answer, not just like typing any random text. Okay, so here now the thing is that we want to discuss some kind of the very specific ideas in terms of how we are achieving this kind of the rotation, the equivariance, the property in the design of each of the layer in the neural network. So what we want to do is that if we see the details of the implementation of each of the layer of the neural net, there are some kind of the multiple parts. So we are first having some kind of the linear layers, and then after that we typically apply the activation function, right? Some kind of something like the ReLU function. And also in the design of the neural network, we also had the pooling layers, having the max pooling in the point net. And obviously for the neural net the architecture, we also have the normalization, like the batch normalization, right? So for all these kind of each of the component in the neural network, we're gonna make some kind of the modification in terms like achieving the rotation, the equivariance. So how we're gonna make some kind of the minimal changes in the neural net design for each of the components is basically what we are going to discuss here. And obviously the thing is that the linear and the non-linear layers, basically the activation functions are basically the function that we are going to apply for each of the point, as we have the shared MLP in the point net design, right? And also the pooling and the normalization are basically some sort of the global functions that are basically applied to the entire point cloud. So those are kind of things. And also what we are going to do is that once we basically design some kind of the some new linear layers and non-linear layers and all the things here, in terms of like achieving the rotation, the equivariance, we are going to directly basically replace the given the layers in the point net with this kind of the some rotation, the equivariance, some kind of functions. So that's basically what we are going to do. So then we can apply these kind of the ideas into not only the point net, but any kind of the variance of the point net in terms of like transforming the given the network into the rotation, the equivariant network. So that's basically what we're going to do. And for the linear layer, actually, this is quite obvious that we can very easily achieve some kind of the rotation, the equivariance, because if we basically multiply any kind of the matrix without the bias term, so typically the linear layer in the MLP is kind of the affine function, right? So we are not only multiplying some kind of the matrix, but also adding some kind of the vectors here. So having some kind of bias term. But if we do not take the bias term, if we only basically multiply some kind of the matrix, then obviously this function becomes a rotation, the equivariant function. Because if we see that, obviously like, it's basically the case that we are multiplying this kind of the W matrix on the left-hand side, and also like applying the rotation is basically multiplying this matrix on the right-hand side. Then basically, if you first rotate all the given the input data and then feed that input to the this kind of linear layer, it becomes the same that you are first basically feeding the input to the linear layer and then applying the rotation the matrix, right? So this is basically quite clear in terms of like achieving the rotation equivariance, right? Yeah. So this is the thing. So if we have any kind of the input data, then we can basically this is basically learned the parameters of the neural network, right? So the kind of the MLP the parameters for each layer, and if we basically multiply this kind of thing without the bias term, then this is the case that we can easily achieve some kind of the rotation equivariance, right? The problem is starting from the non-linear layers. So how are we gonna basically make some kind of the rotation equivariance, some kind of the non-linear layers? So let's think about some kind of the ReLU function, which is the most popular activation function. Everyone knows the ReLU function here, right? Is there anyone who hasn't seen the ReLU function before? So this is basically the function that has been used in the assignments in terms of having the activation function. So typical neural net design is that we are having the linear layer and we are applying some kind of activation function, right? And the ReLU is basically a function that is basically truncating the values with some kind of a half space in a one-dimensional space. So this is the way that we can think about this kind of ReLU function. So what we do with the ReLU function is that we are somehow specifying the half space, which is basically just like setting a threshold in the one-dimensional space, and any value below this kind of the threshold becomes 0, right? So this is the way that we have somehow truncating the values with the half space in the one-dimensional space. And here the question is that how we can do the same thing in the higher dimensional space. How we can make some kind of similar function in the higher dimensional space while achieving the rotation, the equivariance. So this is kind of the question here, right? Do you have any ideas for this? How we can achieve this kind of the some truncation with the half space in the high dimensional space? So basically, we want to do the same thing in terms like doing some kind of the truncation with the half space. But here the thing is that we want to do these things in a kind of like rotation the equivariant way. So what we do is that we first define the half space for each of the points and the channel using the linear layer. So let's think about this case that we are having the input the vector list the picture. And using some kind of the linear layer, we're gonna get some kind of the output, right? So this is kind of the quantity, some of the vectors. We want to apply some kind of the truncation. But we want to basically apply this kind of the truncation with some kind of the some data dependent the half spaces, which is also learned using the rotation, the equivariant the layer. So in that way, we are applying some kind of the another linear layer in terms of learning the half space for each of the point and the channel, right? So we are making another linear layer, which is giving the same form of a set of the vectors, but now we are treating all the vectors as kind of the normal vector for the half space, right? So in the three-dimensional space, you have any kind of the vector that will basically define some kind of the plane and also the half space in the three-dimensional space, right? So now we are treating the output of another linear layer as kind of the normal vectors for the half space. So in this way, we are also learning the half space for each of the point and the channel, also in a kind of rotation, the equivariant way. So that's kind of the key idea, right? Does it make sense? So that's basically the similar thing that what we have done in the 1D case. So in the 1D case, everything is on the same dimension, in the single dimension, right? And here, basically, we set the threshold and truncated all the values below that threshold, right? So that's basically the way that we are defining the half space and also do some kind of truncation. In the three-dimensional space, for the vectors, how we can do that? For the vectors, we want to basically, we cannot define some kind of the half space because we don't know what sort of the rotation we will apply to the input point cloud, right? So that's why we are also learning the half space in a kind of the data-dependent way for each of the point and the channel. And the way that we are learning the data-dependent half space for each of the input is basically using just like simply another linear layer in terms like predicting also a same set of the vectors. But now we are treating these vectors as kind of the normal vector for the half spaces. And then we can do the same, the truncation, some kind of the clipping, using some kind of defined the half space. So basically by checking the angle between the normal direction of the half plane and also the given the feature of the vector, if the angle is basically less than the 90 degree, then we just use the same, the output the vectors. But if the angle is greater than 90 degrees, then we are basically doing some kind of clipping in terms of projecting the feature vector over the plane, the boundary of the half space. So that's basically what we do as kind of a truncation. It is clear? Any questions on this? Yeah. So this is basically the simple idea in terms of like achieving the rotation, the equivariance in the activation function. So here the one major difference with the 1D case, with the Bernoulli pointed at, is that now we are not using the predefined half space, but we are using some kind of the learned half space, which is learned for the so basically given for each of the per point and the channel. And also the half spaces are also predicted using another additional linear layer. So as you can see here, we are having one linear layer, which is predicting the feature vectors, and also another linear layer, which is now defining the half spaces. By combining these two, now we can apply the nonlinear function, which is the truncation function. And this is basically rotation equivariant function because everything was basically rotation equivariant, right? So we are using the same linear layer. And also if we go back to this computation, this is the case that we are taking the dot product here, right, of the two vectors. And the dot product remains as kind of the rotation invariant, right? So however, basically you rotate, the two vectors using the same rotation matrix, the output of the dot product becomes the same, right? So these basically the dot products are basically rotation the invariant with the properties, and everything else is basically rotation the equivariant, right? So in this way, we can guarantee that this operation is also rotation the equivariant. So basically that's the way that we are defining some kind of the activation functions. It's clear. And how about the pulling the layers? So pulling is now some kind of global function, not the per point function, right? So given some kind of a set of some kind of the vectoristic features, how we can also apply the pulling the layers. So if we also think about the PointNet case, so PointNet was the case that we are having the 1,204 dimensional the vectors for each of the point. And then we are basically applying the 1D max pulling for each of the channel, right? And the max pulling is basically the meaning that we are sorting all the scalar values for each of the channel and then selecting the maximum value, right? Does it make sense? Yeah, for each of the channel, we just sorted all the scalar values and pick the maximum value. So that was the case that we are applying some kind of 1D max pulling in the PointNet. And also here the question is that how are we going to do the same thing? How are we going to basically sort the vectors in some kind of certain way? Do you have any ideas for this? As we somehow transformed the regular function in the 1D case into some kind of the truncation in this 3D case, how can you also do the similar things in terms of doing some sort of the sorting in the high dimensional space? So basically, one thing that I want to say is that there can be multiple other ways to do the same thing. Here, basically, we are discussing like one specific way, and this is like also the one specific way that we can minimize some kind of the changes in the neural net architecture. So what we can do is that simply we can also apply the same idea in terms like also learning the direction of the sorting. So as we also have done in the ReLU case, in the activation function case, in that case, we also learned the half spaces for each of the points and the channel using some kind of the additional linear layer, right? And then now what we can do is that we can also learn the direction of kind of the sorting for each of the point and the channel using some another linear layer. So what we are going to do is that using the additional linear layer, now we also predict a set of the vectors like this. And then the quantity that we want to sort is basically the inner product with the given the feature vector, and also this kind of learn some sort of the pivot vector, which is defined for the per point and the channel, right? So now we want to basically pick the vector for each of the channel, which is giving the maximum the inner product for each of the given some sort of the pivot direction vector here. Make sense? Actually here one small the typo is that this K should be, I think, normalized. Yeah, so this is basically the thing. So since we cannot structurally sort the given the vectors, what we do is that we are also somehow defining the direction to be projected, direction to project the given the feature vector into the direction. And then we basically sort all the vectors based on the inner products between the feature vectors and the learned direction, and then pick the best one in terms of the highest the score with the inner products. So that's also what we do in the pooling the layer. It is clear. So yeah, so this is basically what we do in the pooling layers. So then the one remaining thing would be basically normalized layers, right? For the normalization, actually, also there can be multiple ways to basically normalize the input data. So probably if you took some kind of deep learning courses, there are also some kind of various normalization techniques. We can apply some kind of layer normalization or the instant normalization or the batch normalization. So in the case of like just like making something like the point net, the layer normalization is basically defined as kind of like for each of the objects, for each of the point cloud, we normalize the features over all the points and all the channels. So that's the layer normalization. And we can directly apply this idea for the given the vector list features. There's no reason not to apply these kind of things. So this can be directly applicable to the vector neurons. And instant normalization is the case that for each of the objects and also each of the points, we only normalize over the channels, normalizing the features over the channels. So this is also kind of applicable in the vector neural setup. The problem that actually comes when you want to apply some kind of the batch normalization. So basically, the batch normalization is the case like for each of the points with the same index. We want to normalize all the features over the objects and also objects in the batch and also over the channels. So that's basically the batch normalization that we applied in the point net, right? So again, the batch normalization in the case that for each of the point with the same index, we want to apply the normalization of the features over the objects in a batch and the channels. And this is kind of problematic because now the features that we are having is kind of the rotation sensitive features, right? Which means that if you rotate all the 3D objects, all the features in the objects will be also rotated, right? So which means that depending on like what sort of the random arbitrary rotations that you have in the objects in the same batch, the output of the normalization of the batch normalization will be also changed, right? So the output of the batch normalization becomes like sensitive to each of the orientations for the different objects. So which means that the vectors like in the one object can be affected by the rotations that are basically applied to the other objects in the same batch. And that's basically what we don't want to see because like in the previous cases, for the layer normalization, the normalization, these were the cases that we are applying the features in the same object. So we didn't need to basically worry about that we are basically changing the coordinate system for the features that we are having. But these are now the cases that we are normalizing the vector features that are basically presenting some kind of the different coordinate system, right? So basically, how are we gonna properly normalize the vectors living in the different coordinate system is basically what we need to discuss here. So what we want to do is that since all the objects are basically having the different coordinate system, what we want to do is that we want to normalize only the rotation, the invariant properties for the vectors. And the rotation, the invariant properties for the vectors would be basically the vector norms. So instead of like normalizing the entire vectors, we are only normalizing the vector norms and then applying this kind of the normalized norms into the given vectors. Does it make sense? So what we first do is that we are computing the norms of all the vectors and having this kind of the tensors like this. And then now we apply the batch normalization into the norm of the vectors. And now having some kind of the normalized norms, right? And then we scale given the output vectors based on the normalized vector norms. So that's the basic idea for the batch normalization. And this is the same, like when you have some this kind of the vector-list features, now we're having some kind of the norms for each of the vectors and applying the same batch normalization that we typically apply in some kind of typical linear network, and then basically adjusting the scale of each of the vectors based on the normalized norms. So that's what we do. Clear? So one last thing is basically how we can also make some kind of the rotation, the invariant network, right? So these are all the ideas in terms of achieving some kind of the rotation, the equivariant the architectures, right? Based on that, actually we can simply make some kind of the rotation, the invariant architecture as well, in terms of having just like one single layer that can be basically giving some kind of the same output, which is basically agnostic to some kind of rotation that we apply to the input, right? So when you have any kind of the rotation, the equivariant architectures like this, when you have like one single layer of the rotation, achieving the rotation, the invariance, we can also transform the entire network as kind of the rotation, the invariant network. So here the question is that how we can make a single layer of the rotation, the invariance. Also here the key idea is that let's say we are having the two rotation equivariant features, the vector list features given from the same input. We are having the V and the T. Let's say these two are basically the rotation, the equivariant features. Then what we can see is that if we compute V times T transpose, then this becomes rotation the invariant because if we see like this kind of multiplication, then you can see that basically rotations are basically canceled out if you basically compute the V times T transpose. Makes sense? So what this means is that, let's say you have any kind of the input, and using the rotation equivariant layers like this, we can basically get the two outputs, which are basically rotation equivariant features like this. And if you simply compute like V times like T transpose like this, then the output becomes rotation invariant features, right? Which means that whatever the rotation that you apply to this input, the output remains the same. So by just having one single rotation, the invariant layer into the rotation equivariant architectures, at the end, like if we have this layer, then we can easily transform the network into the rotation, the invariant the network. And even like easier way to achieve this is that even you do not have like two neural networks. Let's say you just like copy the input, the rotation equivalent features like this, and have another like one small network like this, multiply these two, and you can get some kind of the features in this some canonical space. So this is the basic idea. Any questions on this? So yeah, by having this kind of rotation invariant layers, we can also make some kind of the classification of the network, which requires the rotation invariance. And without having this layer, we can also make some kind of the segmentation of the network, and we can also make some kind of some reconstruction of the networks as well. So simply in the pointer net, the way that we can transform this into the rotation equivalent architecture would be basically replacing all the pooling and the linear layers, everything in with some the layers that we discussed in the previous slides. And also not only for the pointer net, for any kind of the variant of the pointer like the DGCNN. So this was also the case that as kind of like extension of the pointer net, we basically have some kind of neural network, which is basically now handling the edge information. So when you have some kind of the adjacent points in this 3D space, we are taking some kind of some directional vector from the one point to the other using the neural network, and also treating also processing the coordinates of each of the points as well. Using kind of the two small neural network, and also pulling the edge information. So this was basically the edge convolution that we also discussed in the previous lectures. And also we can simply replace everything here using some kind of some rotation, the equivariant layers, just simply replacing all the linear layer and the non-linear layers, and also the pulling operation in a way to basically achieving the rotation, the equivariance, right? So yeah, this is really kind of interesting, the idea that we can make some kind of changes for each of the layer in terms like achieving the rotation equivariance. Any questions on this? Oh, so let's see some kind of the results. So there are some kind of 3 experiments with the classification. The first case is basically rotating 3D models arbitrarily with some kind of the rotation along the z-axis. And then we are rotating 3D models along the z-axis both in the training time and the test time. So this is like one case. The other case is that we are rotating the 3D models with some kind of the arbitrary 3D rotations both in the training and the test time. Actually, the second case might be like more challenging case in terms of that. In the training time, we only rotate 3D models along the z-axis, not making randomly rotations. But in the test time, we are making some arbitrary 3D rotations. So we are testing whether the neural network can also handle the 3D models with some kind of the rotations that have not used in the training the process as well. So also for some kind of the unseen poses of the 3D models, how robust the neural net would be in terms of like handling this kind of the new data. So these are basically the 3 cases. And if you see the results here, what we can see is that, so this is the case that in the training time, we are rotating 3D models only for the z-axis. But in the test time, we are applying some kind of the arbitrary rotations. So if you see the results of the PointNet and the DGCNN, obviously the performance is really low because for those 2 neural networks, if you start to apply some kind of the arbitrary rotations, then that becomes the case that like the 3D models become some sort of the completely new, some kind of 3D point cloud that has not been observed in the training time. So that's why basically the accuracy becomes very low in those kind of cases. But obviously, in the case of like some transform the PointNet and the DGCNN with the vector neural net layers, obviously these 2 accuracies should be exactly the same, right? Because as you can see, these 2 are the first column and the second column. These 2 are the cases that the network was trained in exactly the same way, using the same set of the training data, but only the test set was changed. But since the PointNet and the DGCNN with these transform divergence with the vector neurons are basically rotation invariant, the output should be exactly the same, which means that the accuracy also should be exactly the same, right? Makes sense? So now you can see that even for the cases like having some sort of the unseen poses, the rotations of the 3D models, the vector neuron PointNet and the vector neuron DGCNN become very robust, like having the high accuracy. And these are also the cases like that we are sort of doing some sort of data augmentation. So for given these 3D models, we are applying some random rotations both in the training and the test time. So we can see that this is the case that we are doing some sort of the data augmentation in the training time. Then now you can see that PointNet and also DGCNN give some kind of the high accuracy. But compared to that, actually the case when you apply the vector neurons, we can achieve even some higher the accuracy with some more efficient the training. So that's also the output that we can see. And also compared to all the previous work, like you did like this kind of the rotation, the equivariance, some kind of the ideas. These basically simple the modification of the PointNet and DGCNN gives some higher the accuracy. So this is really good thing in terms of that. So these are some kind of the very much like specialized the neural network to achieve some kind of the rotation, the equivariance or the invariance, this case, with some kind of very complicated architectures. But by just like making some small changes in each of the layer in the PointNet, actually you can easily apply, achieve this kind of the rotation, the invariance with some high accuracy as well. These are also some results of the segmentation. You can see that the vector neuron, the DGCNN achieves some better the fast accuracy, and also the shape decompletion the cases. You can see that the output becomes like much more like complete compared to some other kind of the cases, like not having the rotation, the invariance, and the equivariance. And these are some of the outputs. So any questions on this? Yeah, so in the summary, basically we discuss the idea in terms like how we can transform the given the PointNet into some kind of the rotation invariant and equivariant architectures, lifting the scalar vectors into the 3-dimensional vector features, And the idea was basically replacing each of the building block of the neural net, some linear layer, random function, max pooling, the batch normalization, into some kind of the rotation, the equivalent layers, in terms of modifying the point net and the DGCNN. And we can easily achieve some kind of the rotation invariance and equivalence in this case. Any questions on this? Okay, cool. So this was the last kind of topic that we are discussing in the class. And as I said, we don't have the lecture on this Wednesday because of the university the entrance exam. So this will be the last lecture of this class in this semester. But we're gonna still have the 2 poster sessions in next week, and we're gonna also remain the steps for the project reviews. So let's briefly wrap up the things that we discussed in this course. So we discussed actually lots of the topics about the 3D data and their representation and the way that how we can process them and how we can also reconstruct 3D the data and also even how we can generate this 3D data. So as kind of a representation, actually we discussed a lot about like all the different representations of the 3D data because what we could see is that there are basically the pros and the cons. So there is no kind of the silver bullet of the representation that can handle all the issues in the 3D data the processing. So depending on which representation you pick, there are basically the pros and the cons. So we discussed the voxels, multiple representation, the point cloud, and the meshes. And also in the beginning, we also discussed some different ways to basically convert like one representation to the other representation. So depending on what's the kind of the input, the representation of the data that you have, you can do this kind of conversion in terms of like taking some kind of the meshes or the implicit function, whatever that we want to see. And we also discussed that the implicit representation is really powerful representation, especially for many kind of the reconstruction and the generation these setups. And we also discussed the siren and the fluidity features, the positioning, positional the encoding in terms like how we can also reconstruct all the fine details in terms like learning the implicit neural representation. And this idea also has to be extended for the NeRF case as well, learning the radiance and the opacity. And also for that, we discussed some kind of the hybrid version of the representations in terms of like combining the voxels into the implicit functions and also having the triplane also and any other things. So also in terms of like the architectures, we discussed some kind of bunch of the encoding and the decoding architectures. So we discussed the PointNet plus, and also the variance, and also some kind of the architecture that we can predict some kind of the implicit function as well. And today also we discussed the rotation, the equivalent architectures, transforming the PointNet into the background neurons. And then we started with discussed some kind of the ideas for the 3D reconstruction. So the beginning was basically how we can also reconstruct the 3D things from the multi-view images. So this was the classical ideas of like applying the structure from motion using some kind of the epiplot geometry that we discussed in the previous lectures. And then we extend this idea to basically discuss the NeRF, which is some kind of the representative technique for the neural rendering, which is having this kind of the some implicit representation for these 3D models, learn some kind of the multi-view images, which was giving some very high quality the outputs. And then we also started to discuss some kind of the few shot and the zero shot cases, even when you have some kind of the very few number of images, how we can do some kind of some NeRF reconstruction, even with some kind of single image, how we can do the NeRF reconstruction, even without any kind of images, when you only have the prompt, some kind of text information, how we can even make some kind of generation of the 3D. So those kind of things that we discussed. And to properly generate some kind of all these 3D things, we also discussed the idea of the diffusion the models, having the reverse process and the forward process. And at the end of the whole discussion for the diffusion the models, we also discussed the score distillation, the sampling that can be used as kind of the guidance in terms of checking whether the rendered images are real or the fake in the 3D generation. And this could be basically incorporated into the NeRF pipeline in terms like not doing just like 3D reconstruction, but the 3D generation. And then we also discussed some of the ideas for this 3D detection and the segmentation, some kind of the applications of this 3D processing. So would it be like everything for these 3D things? Like what would be kind of some remaining questions? Do you have any kind of the remaining questions here? What are the things that actually there are lots of the topics that we also couldn't cover in this class. And also we discussed lots of the representations of the 3D data. But still, well, I mean, all the 3D representation that we discussed may not be still the perfect representations for the many aspects. So we discussed some ideas in terms of how we can do some kind of the reconstruction and the generation and doing some kind of segmentation of the detection of the things. But actually, there are also tons of the other applications with the 3D data. So we may want to not only reconstruct, generate some kind of 3D object world scenes, but we want to apply some kind of the deformations, right? Especially for some kind of many kind of the cases, making some kind of the 3D contents. We might want to make some kind of interface where the users basically giving some kind of inputs in terms of making some of the changes. For those kind of the cases, like making some deformation in the editing, like having the NURB representation actually may not be the ideal case, because as you can see, like having the implicit function is really kind of the bad option if you want to make some kind of the modification. So if you want to basically stretch some parts, like lift up some parts, like how we can do these kind of things with the NURB representation. So that can be kind of the limitations, like having the NURB representation. While the NURB can be really good representation for the reconstruction and the generation. So how are we gonna basically allow this kind of the deformation and the editing the process to be much basically easier with this kind of the given the pipeline might be one remaining the question. And also one thing that we couldn't discuss that much in this kind of in this class was basically the ideas about like how we can handle some kind of the dynamic scenes and also some kind of articulations. So when you have this kind of the human bodies or some kind of the animal shapes, how we can properly basically reconstruct all the emotions of this kind of some dynamic object and the scenes using some kind of the NURB pipeline or some 3D generation pipeline might be also really the challenging the programs. And there are lots of some very recent ideas like handling those kind of things. So you might want to also check this out. And also for many kinds of 3D things, we want to disentangle some information about the geometry and the appearance, right? If you see many kinds of 3D models, typically the 3D models are basically represented with some kind of the meshes that are basically describing the geometry, and then some texture or some kind of the material information that defines some kind of some materials of the appearance of the 3D objects. So if we basically disentangle the geometry and the appearance, then we can do this kind of editing. Given some kind of same 3D objects, we are only changing the appearance information, right? Or we transfer the appearance information to the other 3D models. So how we can do this kind of disentangling of the geometry and the appearance and doing this kind of separate the editing the process with some kind of given some reconstruction and the generation the pipeline might be also kind of the remaining the question. And also for many 3D objects, there are some kind of certain structure that we can see. As we humans, we can see that there are lots of kind of structures like having some flat planes, having some kind of parallel lines, having some cylinder shape or some cone shape, like having some parallel planes as well. So these are kind of the structures that we humans can basically perceive from many kind of the 3D objects in the scenes. But for typical 3D generation and the reconstruction, we do not incorporate this kind of some structural information, right? Which can be actually very crucial in many kind of the editing the setup. So how we can do incorporate this kind of some structural information in the reconstruction and the generation might be also really important the topic. And also, how about the 3D generation? So we also discussed some kind of the interesting idea in terms of like basically how we do some Gaussian NURB with some kind of the pre-trained diffusion model. So this was kind of interesting the idea, which was also giving some very impressive outputs in terms of making some very diverse 3D shapes. But actually, we did not discuss that much about the limitation of this kind of idea. So can you guess like why we see this kind of some outputs and also some failures here? So these are basically the outputs, basically making the 3D the shapes using the NURB plus this core distillation, the sampling in the Dream Fusion the pipeline. So we are having the NURB and checking the plausibility of the rendered images using the pre-trained diffusion models using the SDS, the loss.
then the typical delimitation, the failure cases that we can see is basically having this kind of cases. That you can see that you can see the face of the rabbit from the multiple views, and also you are having the multiple the same part of the parts like this. We know that these are basically some unrealistic cases. But the reason that we are having this kind of failures, these are really typical failures. So I recommend you to try to just like run the Dream Fusion pipeline yourself and see what you get. Then you can see that actually these are really typical failure cases. And this kind of makes sense because like when you see each of the some 2D images, each of the 2D images might look realistic, but we are seeing the failures because we are rotating the 3D models, right? So we are only having some prior information about the realistic 2D images, but not having utilized any kind of the prior information for the realistic 3D models. And this kind of the red of the 3D priors about the prior for the realistic 3D shapes is basically making this kind of the failure cases. So here the kind of the some future things that we need to do for the 3D generation might be that while still utilizing this kind of the priors coming from the 2D images, we might still need to somehow incorporate some of the prior knowledge about the 3D shapes as well in terms of like resolving this kind of the failure cases. By the way, these failure cases are basically very famous, which has the name, which is the Janus problem, having some multiple faces of the human the face. So we are having this kind of failure cases. To resolve this kind of issues, we might need to incorporate not only the 2D priors, but also the 3D priors as well, in terms like giving some prior information for these 3D models as well. The thing is that we are having more than 5 billion images as kind of the internet scale, the image data set. For the 3D models, the biggest data set is still like 10 million, which is way smaller than scale of the images. But when you basically combine these two information, we're gonna have some much stronger the information in terms of generate some kind of more realistic 3D models. So there are also very recent work incorporating some of these kind of 3D priors. For example, this is like one example that we are utilizing some kind of camera pose information. So when you have a kind of single view image, we are generating some other view images using this kind of diffusion model, which is not only taking the source view images, but also taking the camera pose information as well. So by incorporating this kind of like the camera pose information, we might be able to basically generate the images, which is like the more the consistent across the different views. And this kind of diffusion model can be trained only when we have this kind of the camera pose information for the multi-view images. So this is like one kind of the way that we can provide some sort of the weak supervision for this 3D information. So having some multi-view images and the camera pose. So this might be kind of like one simple way. And there is also another kind of the way to basically more directly combine these 2D and the 3D priors. So this is the case that when you have the Dream Fusion, the pipeline, we are also applying some kind of the 3D diffusion as well. So basically combining the 2D diffusion and the 3D diffusion in terms of basically making some more plausible 3D shapes using the 3D priors, and also adding some kind of the appearance information using some kind of 2D priors. So this can be also another way to basically combine the 2D and the 3D priors, some more realistic 3D generation. So what I expect to see is that probably in the next year, we're gonna see some kind of the new techniques that is really making some realistic, some 3D the contents. So there might be Midjourney 3D or Stable Diffusion 3D, and we're gonna see some more kind of the advanced techniques maybe next year. And also some other courses is that we also discuss lots of the rendering techniques, especially for the neural rendering. And if you are interested in more some kind of the advanced some rendering the pipeline, I'm going to teach this course, the graduate level, the computer graphics course next spring semester. So this course might be good for you if you are more interested in some kind of some advanced rendering the equations. And also for some more details about some geometric processing in terms of like conversion into some other data representation, and also for more some classical ways to handle this kind of some geometric data. Probably, I'm not 100% sure, but probably in the 2025 in the spring semester, I'm also gonna teach this course, geometry modeling the processing. And this would be the course that we are going to discuss more classical ideas in terms of like dealing with some of the geometric data. So this is the end of like this class, and also the things that we're gonna have the two poster sessions next Monday and the Wednesday in the next week. So please check out all the guidelines for the post sessions before you join these sessions. And at the end of like this class, I'd like to ask you to participate 2 surveys. So the one survey about the use cases of the generative AI tools. So as I mentioned multiple times, we strongly even encourage you to basically use all the generative AI tools like ChatGPT, Copilot, all the things for everything, for the writing, the reports, for the assignments, for the projects. So actually, I would like to ask you how much this kind of the generative AI tools were helpful for this kind of the tasks. So please participate in the survey. Our team just like post the link for this survey. So any inputs will be really helpful for the next time of this course. And also, if you have any questions, comments about anything, any feedback for this course, we also have another survey, which is the post-lecture survey. And this is the anonymous survey. So you can basically put any comments, any feedback for this course. So any also feedback for this course will be really helpful. Okay, any questions on this? Okay, so this is the end of this class. So thank you all for basically joining all the lectures. And I will see you in person in the poster sessions next week. Okay. Thank you. Bye.